Okay, let's start. So in the last class we briefly saw how things are made on a CMOS process, and we essentially saw that in practice if you have multiple identical components there will be mismatch among the components, and we have both random and process variations. So to summarize or to make sure that point is clear, let us say you have one particular chip with 1000 identical components, let's say resistors, and if you plot the values of all the resistors and look at its distribution, it will be Gaussian like this, centered around the mean value R0. So this variation within a particular chip is what we call as random mismatch. Okay. Now if you take the mean value of all the resistors from one chip to other chip, so those mean values will also show variation, and that can be anywhere between 10 to 20% from this nominal mean, and this is what we refer to as process variation. And in practice, the process variation happening for MOSFETs, we give some special names. So depending on the fact that depending on whether the MOSFETs are all coming in with the nominal value, or whether the parameters are such that the MOSFET is slow or fast, we define 3 different corners, and with the combination of NMOS PMOS we define 5 worst case corners: slow, fast, the typical or the nominal corner, and fast NMOS, slow PMOS, or slow NMOS, fast PMOS. So these are the 5 extreme corners we typically deal with. Great. And then we looked at how to quantify this random mismatch. Again, if I look at this distribution, it's some R0 plus delta R, and we are interested in quantifying this random mismatch. It's a statistical quantity, so we look at only mean and variance. So mean of delta R is 0, so we only look at the standard deviation sigma delta R. But here again we notice that if I just look at the absolute value of delta R and look at its standard deviation, it is not a very good measure, because if I increase the nominal value, the variation in the resistance value will also increase. So what do we look at instead of looking at the absolute mismatch? Yeah, we look at the mismatch normalized with respect to the nominal value, and this is essentially sigma of delta R by R. Again, this is essentially what I am saying is expectation of some random number x scaled by a constant, the same as taking the expected value of the random number divided by the constant. That's all. And the same way we use for capacitance also, for resistors sigma delta R by R, capacitance sigma delta C by C, relative mismatch. For MOSFETs, the current factor mismatch is again normalized, but the threshold voltage variation we don't normalize, because if you do this, you will find sometimes the threshold voltage of transistors nominally itself might be close to 0, so this quantity blows up, doesn't make sense, so we don't normalize threshold. And it turns out all of these quantities, they are inversely proportional to square root of area. Of course, if you guys figured out this first, you could have given this your name, but unfortunately Marcel Pelgrom observed this, and because of this is referred to as Pelgrom's model. So this straight away gives you one technique to reduce the mismatch in your circuit. So if you want to reduce the mismatch between any two components, what do you do to the area? That's a brute force solution. Anytime you want to reduce mismatch, one straight brute force solution is to increase the area. Okay. Great. So now that we have understood some basics on this random mismatch, let's calculate, or let's see how we might deal with mismatch and calculate what is the effect of this in our circuits. And for that I'll take an example of a current mirror, a simple but classic circuit, but relies heavily on matching between transistors. So let us say this is something, and we try to mirror the current in this branch. Now if this current is I0, what can you say about the current in this branch? I0? I mean, yeah, remember, technically speaking, the current also depends on the VDS of the two transistors. Let's ignore the fact that the current depends on VDS, so that we don't have to deal with it now. So I'll ignore lambda. So the current is ideally equal to I0 here also. Okay. But as we just saw, these two transistors will have mismatches that could be both in threshold voltage as well as in that current factor, that mu CoX W by L. So let's take a case where this left side transistor has a threshold voltage VTH, but this fellow is not having the same threshold. It is VTH plus a delta VTH. Similarly, let's say the current factor here is beta, here it's beta plus delta beta. So now what will be the current in the right side branch? Will it be I0? Will it be I0 if this is a mismatch? No. So this is going to be I0 plus some delta I. So once again, we are interested to quantify what is the mismatch delta I. So again, the mean of this random quantity is 0. Only standard deviation matters. So this is what I might be interested. But once again, remember, if I look at the absolute value, that is not a great quantity to look at, because if I increase the nominal current, even the mismatch in the current increases. So what do we do instead? What do we do? Yeah, we divide by I0. So I'll find this. So this is the quantity I'm interested to find in the circuit. That's all. So let's see how we might go about doing it. Of course, one brute force way is the following. You know that the current in this transistor is I0 plus delta I, and you know what is the current in this transistor? It is the beta of this transistor times VGS minus this VTH, the whole square. So you will get some square law thingy, and then you can expand things, and eventually you will find that your delta I will be a function of delta VTH and delta beta, right? And I mean, this is going to be a square law relation, so we'll have both linear and second order term. So you might get something like delta VTH times something plus delta beta times something. What are the terms you might get? I mean, remember, I am going to do VGS minus VTH the whole square, right? So what are the possible terms you may get? Can you tell me directly? You will also get a term with delta VTH whole square and delta VTH times delta beta. These are the terms you will get. Make sense? So, but remember that all these mismatches are going to be very small in practice. That is, these deltas are going to be very small. If that is the case, how can you approximate this further? We'll take only the first order terms. I'll say that all these second order terms are ignored. This is the same thing you do with your small signal calculation, right? You ignore all the higher order terms and say that I'll only look at the first order terms. That's very good in practice. So which means now you can find that my delta I depends on delta VTH into something plus delta beta times something. So I can find the effect of delta I due to each of these two independently now, right? That is, I'll take first only delta VTH, ignore delta beta 0, find what is delta I. Then what do I do? Yeah, I'll assume delta VTH to be 0, consider only delta beta and find delta I. That gives the complete delta. This is again the same superposition that we are able to do because we are again ignoring all the nonlinear terms. So this has become a linear system. So let's do that. So first let me compute delta I only due to delta VTH, and for this I'll ignore delta beta to be 0. Let me take this once. This is the circuit. So here beta, there is no error. So let's see how we might go about solving this in an easier way. See, tell me this. In a MOS transistor, the drain current depends on what quantity? I mean, the drain current in a transistor majorly depends on which quantity? VGS, or strictly it is VGS minus VTH, right? So it is a function of, I would say, the drain current depends on VGS minus VTH, right? So as of now you see that the threshold voltage is not VTH, so there is a variation. So it is, let us say, VTH plus delta VTH. Right. So to simplify or for ease of understanding, we can treat this in the following fashion. I'll assume that the threshold voltage of the transistor is still VTH. Okay, but this extra delta VTH is an increment added to your VGS. Both are same. So what I'm saying is this, I'll rewrite it like this. It is VGS, so minus a delta VTH adding to the VGS. Both will give the same result, right? So which means now I assume that the two transistors are matched. The delta VTH mismatch I'll have to add by making sure that the gate voltage for this transistor is different from this gate voltage by delta VTH. And how do I model that now? You put a voltage source in between the gates so that the gate voltage is dropped appropriately. So this should be the polarity. Again, the actual polarity doesn't matter because finally you are only interested in standard deviation and variance, so those don't matter. But once you assume some sign, stick to it throughout your calculation. So now tell me, if delta VTH is 0, both gates are equal, what is the drain current here? I0. Now what I am saying is the gate voltage of the right side transistor has a small increment minus delta VTH. Then what is the incremental change in the current delta I? That's all. I mean, can you be careful? Is it GM times delta I or? Yeah, minus GM times delta VTH. That's all. So which means my delta I due to delta VTH is simply minus GM delta VTH. That's it. But I am not interested in delta I am interested in delta I by I0. So if I scale this by I0, this is what I get. So that's just half the job. I have just considered the effect of delta VTH. Now let's look at the effect of delta beta. But before that, is this fine? The way we model delta VTH mismatch? The idea is to assume that the threshold voltages are identical, but the threshold mismatch is modeled as a change in your effective VGS. That's all. So then let's look at the effect of delta beta. I'll take the same. Now I'll assume that VTH is fine, but beta is the issue. So this is delta I due to delta beta. So here we can easily write this is the current I0 plus delta I, and this current is the current factor beta plus delta beta times VGS minus VTH whole square. So that I'll say it as the overdrive voltage whole square. So this now I can expand. This is beta times the overdrive square plus delta beta times V overdrive square. What is this term beta times overdrive square? That is I0. So which means this to go off. So that directly gives you delta I to be delta beta times V overdrive square. And you can simplify this further. So I'll say that I'll divide this by beta, multiply this by beta. So how do you simplify this further now? Delta beta by beta times so which means to model this beta mismatch, the current factor mismatch, in practice we can do the following. As usual, we'll assume that there is no mismatch in the transistors, that is, this also has the same beta. But how do I model this delta I now here in the circuit? As of now, the current flowing in the transistor is what? I0, but it should be I0 plus delta I. So how do I model that now? You should put another. What should I put? I mean, is the question clear? The idea is what I don't want to have delta beta here. I want to consider that the transistors are matched so that calculations are easier. But I know that I have a delta I current. So how should I change, or what should I include in this to model this additional current delta I? I mean, I can put another current source delta I, right? That's all. Fine. And this delta I, you know what is it? It is delta beta by beta times the nominal current I know. That's what you should do. So again, I'm not interested in delta I finally. I want delta I by I naught. So if I do this, it just becomes delta beta by beta. So let me write the total delta I by I naught. Due to the threshold voltage mismatch, the expression we saw was minus Gm by I times delta Vth. So this is minus Gm by I naught times delta Vth. Due to the beta mismatch, it is delta beta by beta. So finally, what quantity I am interested in? I am not interested in this random number. What parameter of the random number I am interested? Standard deviation. So let's first look at the variance. So tell me, what is the variance of this sum? All your probability random process. Okay, great. Let us say I have, what can you say about the mean of all these quantities? If the mean is 0, what can you say about the variance and mean square? Both are? Okay. Remember that variance is expected value of the quantity minus the mean square. Mean is 0, so this is same as expected value of square. Right? So essentially I am taking the mean of the squared quantity, that is same as the variance. So now all I have is expected value of some 2 x1 plus x2 whole square. What is this equal to? Expected value of x1 square plus this 2 times x1 x2. Now if I say that the delta Vth, delta beta are independent, which is in fact the case, they have no correlation. Let us say they are not, I will not say correlation, they are independent. If the two variables are independent, how can you simplify this? 0, is it? It is product of the individual expectations. Okay, what you are saying is true if the variables are not correlated. Independence and uncorrelation are two different things. But what can you say about, in this case, what can you say about the individual expectations? 0. The quantities are all 0 mean, so which means each of them go to 0. So which means if I want to find expected, mean squared value of the sum, it is essentially sum of the individual mean squares. This is true if you have 0 mean independent random variables. Okay, two things are happening. They are independent and 0 mean. I'm sure this is not, hopefully this is not the first time you are hearing these things. Even if it's that case, it's okay. We will not deal with it a lot. So now tell me, what is the mean squared value for this? Gm by naught whole square times sigma square of delta Vth. It is the sum of the individual mean squared values, a constant that gets squared directly, and then sigma square of this plus sigma square of, it's the same thing. 1 by beta square of sigma square of delta beta is same as sigma square of delta beta by beta. Okay, so let me take this. So this is the final expression we have. Oops. Yeah. Okay. So here let's make sense of the expressions. And okay, before that let me write it. So remember, this is Gm by A naught whole square. And Marcel Pelgrom already told you this is inversely proportional to area, right? that is all the sigma quantities are inversely proportional to square root of area. So this I can write it as some constant a VTH square by WL plus some a beta square times by W. Okay. So now tell me, if you want to reduce the effect of the beta mismatch, what is the solution? What can you do? The only solution is, this is beta mismatch. The only solution is go and increase the area. There is no other knob you have to play with. This is the term corresponding to the VTH mismatch. Here, of course, to reduce the mismatch, you can increase the area. What is the other knob you have? Yeah, or I mean, it's GM by naught should be lower or higher? Lower. And remember, we already know usually we can bias our transistors in strong inversion or in weak inversion. Now, if this is your concern, which region would you bias your transistor in? You want to have a very small GM by I naught. Would you prefer strong or weak inversion? Strong inversion. So which means you bias in strong inversion. That is, if your main concern is to reduce the mismatch in the transistors, especially the VTH mismatch, strong inversion is the way to. So that's another reason why we prefer biasing transistors in strong inversion and not in weak inversion. Okay, so now if you are biasing in strong inversion, what can you say about the overdrive voltage? Is it higher or lower? Higher. VGS is larger, so higher. So now tell me, does it make sense that if I have a larger overdrive voltage, changes in threshold voltage is not so significant? Yeah, why? I mean, forget about the fact that, you know, this GM by ID blah blah blah. Logically speaking, does it make sense to you that if I increase my overdrive voltage, any changes in the threshold voltage is not significant? Does it make sense logically? Yeah, your unit is, yeah, why? Yeah, if you're getting, let's say, if your overdrive voltage is 500 millivolts, for example, another case, let's say it's 100 millivolt. If threshold voltage changes by 50 millivolt, the effective overdrive will be reduced a lot in this case, whereas here it is not. It's like stealing 1 rupee from 10 rupees, so it's 1 rupee from 1000 rupees. It's like, you know, if 100 rupees falls from our pocket, we'll make sure we bend down and take it. But if, let's say, the same happens for Ambani or Adani, by the time they bend and take it, their worth increases by 100 crores. They might not even mind doing it, right? Same thing. Okay, so this is it. So the bottom line is this: if we have threshold voltage mismatch, the way we deal with, or the way we analyze the effect is this way. We make sure that the transistors are assumed to be having the same threshold, but the delta VTH is modeled as an increment in the gate. Similarly, if we have a delta beta mismatch or beta mismatch, again you model the effect as an additive current source at the drain. And in practice, it turns out in most cases this VTH mismatch is the dominant compared to this one. So mostly now, if I deal with mismatch, we'll mostly look at only VTH mismatch, because typically that's what is dominant in transistors.